It's my pleasure to welcome you all for today's talk. And today we have the privilege to have Professor Fall from Senegal that will give us a talk. Professor Fall is a member of our editorial board. So I take the opportunity to thank him for all these great service that he has been given to the journal. So with no further ado, Professor Fall, the floor is yours, and I look forward to your talk.
Thank you very much, Eduardo. Thank you also, Jan Stanley. So I think without you, so I would not say we can do what we are doing in the journal. And thank you also for the invitation. Let me just start sharing my screen and slides so that we can go directly to the talk. And so I am going to talk about constant, non-local mean curvature surfaces. So even if the seminar is meant for SNPDs, but this is related to PDs, and so somehow PDs which are non-local and maybe of fractional order. So these are geometric problems, but in general, so we use PD tools to solve the geometric problems that we want to solve. So here, I just recall. So maybe if we forget about non-local, so we have just constant mean curvature surfaces, and so constant here, I mean constant but non-zero. In general, for surfaces with zero mean curvature, so people call them minimal surface. But still they are constant mean curvature surfaces. But in general, so when we consider only constant mean curvature surfaces, we mean those which have non-zero and constant mean curvature. And this is the subject of the talk of today. And there are very few of them, very few constant non-local mean curvature surfaces that have been found so far. Maybe it's not just because they are hard to find, but also people start studying them only very recently. So these are since there are not too many results, so it's very easy to present all the results that have been obtained so far. And I will also describe different open problems that comes to this. Let me just start maybe by recalling some questions or maybe some properties and some surfaces with constant but classical mean curvature. So the study of these questions dated several years ago, and somehow there were very few surfaces that were known which are minimal somehow. Sometimes it's very easy to build them using soft films. So for instance, the catenoid was known since many years ago, the helicoid and the plane. But then, so there are many surfaces that can be also constructed by soft film, but there are those which can be constructed without soft films. And this is where, somehow, geometric measure theory, complex analysis, PDs are needed somehow in order to know if there are others which we can see from soft films or not. And so, according to my knowledge, so the first one was found by Costa, so the Brazilian mathematician, so in 1982, who obtained this embedded minimal surface with genus. And so this also triggered many research in this direction. So the existence of minimal surfaces. So in a sense, those which cannot be seen from by making just simple soft films. Okay, so what are the properties? So these surfaces, so they have very interesting properties that somehow they comes from energy minimization. So mainly, if you look at those which come from soft films, there is an energy, so which is kind of minimized in order to obtain this type of equilibrium, this type of configuration of an interface, so which separate the space. And so this energy is nothing but how proportional to the area of surface that we see. And once you minimize this, then you obtain a geometric quantity, and that geometric quantity, which of course should vanish if you do not add any constraints, and that geometric quantity is the area functional. And this is somehow what I'm just saying here. So the area, so when you look at a surface, so if you look at the interface that we see so far, then if you look at locally, each so the area are minimizing so locally, and in some cases, if you, for example, if the catenate you can obtain by minimization, but you restrict yourself on some rotational symmetric surfaces, and these are called minimal surface. So in the literature, it's not, but in the literature, so not only those with minimized area, but those which have zero mean curvature. So I'll just say what the mean curvature is now. And also they are, of course, some of them are also solution to the famous Plato's problem. So with somehow to say, okay, so give me a wire, so give me somehow a simply connected curve. So can I find a minimal surface which span for which the boundary is somehow the wire? And you see somehow if you have two connected circles, maybe planes, two connected circles which are parallel, then you put it in a soft film, then you can only see a catenate, and this is somehow very interesting. So so experiments can tell us, but it's not in general easy just to solve the problem. In fact, this Plato problem was solved by Rado and Douglas, and so because of that, Douglas obtained a field medal. So if you look at the area, so maybe we can simply say, okay, so let me just write sigma is an orientable smooth surface, so for which the normal is nu. Then I perturb the surface a little bit, and then I look at how the area changes, so how the volume of the sigma of the hypersurface sigma changes. And when I look at the variation of area, so then I have this nice geometric quantities, so which is called in general H sigma, which is defined on sigma. So there is a typos here. Oops. So this is just sorry for the So this is just the integral of the hypersurface, and which is and so if you have the variation vector field V, then you will get the normal direction of the normal part of the variation vector field V, so which is V times nu, and so this is just so if you look at the normal direction of the variation of area gives the mean curvature, which is a nice geometric quantity. And so since now, as I said before, so those which are called minimal surfaces, though they are some are critical points of the area functional, some they do minimize. Then so the mean curvature is zero, and in fact, all these surfaces they satisfy this property. But if you add some constraint, so which means unclosed volume constraints or global or locally, then you obtain a surface with constant mean curvature. So of course, maybe so from the isoperimetric inequality, so if the surface is compact, then you know what is it, but you may not see, you may have those for which maybe you can just locally so put constraint, volume constraint, and in this case you have so you have a constant mean curvature surface. So for instance, if you consider the cylinder and many surfaces, so they have constant mean curvature surfaces which are non-zero. Okay, so so perhaps many of you know, so but there is an interesting PD expression for the mean curvature of a surface when it is given by the graph of function, and in this case, so it's thus you integrate the constant function with respect to the volume element. The volume element is the square root of the 1 plus gradient u squared, and therefore you get your surface. And in this case, perturbing a little bit the surface, you just perturb the graph, and you look at the first variation, so which should correspond, of course, to the mean curvature, as we said before. But then in this case, so when you compute, so you obtain this usual expression that is quite famous, the divergence of the gradient of u square root of 1 plus grad u squared, and which is exactly the mean curvature of a hypersurface given by a graph. And this is a quasilinear PD, which is very interesting. Somehow maximum principles can be used, so many different techniques from PDs can be used. Maybe kind of Bernstein type results, many kind of results somehow can be used, can be proved by looking at the PDs. So as I said, so it's a quasi-linear PD, and if you look at maybe all these surfaces, locally they are graphs, and locally they, when the graph solves the equation, this quasi-linear PD, and of course many people also, maybe as you may know, many quasi-linear PD, they don't have a unique solution. In some cases, you can have a unique solution, but you have to perhaps maybe do a lot of restriction, maybe adding symmetry and things like that. But in general, you don't have uniqueness. And also somehow this PD expression can be useful. For instance, if you wanted to look at the 1D case, then you can only see that your solution is an affine function, which is the usual, the classical theory that we know from the Dirichlet problem, that somehow, you can find geodesics by minimizing the lengths among all curves separating 2 points, and in the Euclidean space, somehow these are lines. Okay, so if we wanted to understand now, this was just a recall on the non-local mean curvature, on the classical mean curvature, and the area functional, the classical area functional. So the classical area functional. Let me just write, which also can be seen from. So maybe we can say here, so consider omega, and then so the classical area functional can be also seen by, oh, so this is not working today. So by just looking at the, I don't know what happened today. Sorry. So let me stop this. So by just looking at the total energy of the area of the total energy of the gradient of a function, but for the fractional case, you don't look at the gradient, but you look at the fractional semi-norm. And when you look at the fractional semi-norm, if the set E is somehow bounded, then this is somehow what you see here, and which is what is called the fractional perimeter, non-local perimeter, or the fractional perimeter of order alpha. And so this was studied. So somehow this non kind of interaction between in and inside of a set, have been studied also. So some years ago, but not with this, inverse square the power of x minus y, but maybe but with interactions which are exponentially decaying or things like that. And so this was studied several years ago by many researchers, and when they were interested in non-local models in phase transitions in solids. And so if you see here, so the second expression of the fractional perimeter, this is quite interesting to see that in fact we are just looking at the semi-norm of the characteristic function. Which is something, so big for alpha is smaller than 1, so which is something that you cannot do in the classical case, because the gradient of the characteristic function, so it will not make any sense somehow, and then you have to go into functions with bounded variations. And there you have a topology, and you can use the minimization argument and to obtain sets which minimize somehow the total energy which is given by the semi-norm of the bounded variation of the function, so with the BV semi-norm. But in the fractional case, you do not need to define BV, of course, but you can simply just look at the semi-norm of the characteristic function. And it has somehow also a kind of localized form, and such a localized form allows somehow to set up a plateau problem. So in a sense, so you do not so in a sense you wanted to prescribe a boundary value. So in a sense, the plateau problem is that, so give me a wire or give me a curve, then I find a hypersurface which is minimal, so with zero mean curvature, or maybe which minimize the energy, and which for which the boundary is given by the curve, by the closed curve that I am having. Well, in the non-local setting, so the problem is there is so many interaction that a boundary condition, a single boundary condition would not make sense. And therefore, so one has to look at what the boundary condition should be. And in this fractional setting, so the boundary condition is somehow an exterior boundary condition. And once you are able to know which type of problem you should prescribe, then you can build up your energy, and which is this localized fractional perimeter of a set E inside omega. So in a sense, when you fix omega, you wanted to minimize part of the fractional area of the set inside omega, and in the exterior of omega, then I wanted to prescribe a set, so which is exactly a plateau problem. And in fact, so this expression is a nice thing to see that when I send alpha to 1, then I recover the classical area functional. So which means I can see a kind of approximation of the BV semi-norm, or the bounded variation semi-norm of the characteristic function by the fractional perimeter. And this was studied, in fact, several years ago by Davila. So there are works of Caffarelli, Valdinotti, so Ambrosio, De Filippis, and Martinazzi. Who studied gamma convergence as alpha is converging to 1. But still, even if the work of Davila, who was answering a question of Brazis, showed that in fact, if alpha converges to 1, then I converges to the total variation, or maybe the BV semi-norm of the set E. But still, the study of this plateau problem is very recent and was first studied by Caffarelli, Rockjoff, and Savin in 2010, who proved the existence and somehow regularity of the solutions. But in terms of regularity, most of the results are known. Some results are known, but they are not really completely well understood, and several open problems are left in this research direction. So once you have an energy, of course, what you in general do is very natural, is to look at what are the equilibrium hypersurfaces, or maybe the equilibrium sets that I obtain. So when I compute my first variation, or maybe the first derivative, that in this case it is possible to do. And if you do it, so you have a nice geometric quantity which depend on the set, and which comes in the normal part, which is proportional to the normal part when I shake a set. So when I shake any set which is sufficiently regular. And this quantity is exactly what is known as the non-local mean curvature or fractional mean curvature. But then how it looks like, this is the question. Okay, so if you remember very well, so in the case of the classical mean curvature, so we have an expression that we cannot say what is it, of course, but we can say what is it when I act on graphs. I know that it's sum of principal curvatures, but still to go and look for principal curvatures, again, it's a long way. But if you really want to use PDs and things like that, it's perhaps more common, more convenient to find out a kind of representation that are easy to use. And then, so what is it, this geometric quantity? So let me just recall another expression, so which is the one of the mean curvature, so which is not the one that which is exactly, so which is not different, of course, but somehow also nice to see, nice to understand that it's in fact the divergence of the norm, of the extension of the normal. So it's the divergence in Rn of the normal, which is extended from the boundary inside the set. And this is the normalized version. So the 1 over n minus 1 is just a normalization, which somehow also shows that, in fact, it depends on the orientation you choose. So if you look at from inside or from outside, so the mean curvature changes just a sign. So it is an extrinsic, of course, geometric quantity, but it's not intrinsic, like the Gauss curvature or things like that. So the non-local mean curvature itself, it is a kind of non-local divergence, but is somehow where you can measure angles between y minus x and the normal, and then you sum over the whole surface weighted by y minus x. And in a sense, if you so the interaction, so in general, you can simply write this as a kind of short range and long range quantities. So just by cutting off around x, and then you separate the two sums inside. So in a ball centered at x, in the exterior of the ball centered at x, and so you see kind of short range and long range interaction. And in a ball centered at x, so if you see maybe if alpha is becoming close to 1, then you are nearly close somehow to the divergence of the normal. So which is quite interesting, and I will come back to this later. So the non-local mean curvature, not of course this form, but it's appeared first in the work of Kafferli-Souganidis in 2008, and also later in the work of Kafferli, Rockjoff, and Savi. So this expression, so we have to keep it in mind. It's an interesting expression of the non-local mean curvature. Sometimes very good to use, but sometimes not nice to use, exactly as the one of the mean curvature. So you see very rarely that people use this expression. But yeah, so if you want to make, of course, comparison principle, I don't think this will be the good expression to use. But if you write it as graph locally, then you see that it's very nice because you have a quasi-linear PD, so a divergence type operator, and you know how to deal with the difference of the mean curvature of two surfaces which touch together. So there is another symplectic expression of the mean curvature or non-local mean curvature. So which I call symplectic. So it's kind of very simple expression, but it turns out that it is nicer. It is nicer in the non-local case, and we can see that. So let me just consider the sign, the indicator function. So which is the function that is -1 if I'm in the set E, and +1 if I'm in the exterior of the set. And somehow I can also write down the mean curvature at any point at the boundary by just doing this average of the tau function, of the indicator function, the signed one, of course. So in a sense, I'm just looking at the infinitesimal and kind of infinitesimal averaging, so near the boundary. And this is, of course, well-defined because, if at x, the hypersurface, so the boundary of the set E is smooth enough, which means it's nearly flat. So I almost have the same number of -1 and +1s. And so, which means I have a lot of cancellations. And this is the reason why, so you in fact, when you can average and again divide by so epsilon in order to see the remainder after you kill together the +1s and the -1s. So in a sense, you can measure how the boundary of the set is curved at x, so by just doing an averaging. And of course, so maybe you know also that in fact in physical terms also the mean curvature is proportional to the pressure difference between two non-mixed fluids. But then what about the fractional mean curvature? So the fractional mean curvature is exactly just a weighted integral over the whole space of this signed indicator function. So which is somehow I have, which is also a kind of, which can be also right in terms of somehow a short and long range path, and so there is, so the interaction somehow is becoming much stronger if y is close to x, because you see if y is close to x, so the integral is very singular. But even if this is the case, since you are considering the signed indicator function, you still have a lot of cancellations if the boundary of the set E is regular enough. And in that case, so maybe if you look at the principal value integral, which is the PV that we write here, so you have a lot of cancellations that allows you to obtain a value which is finite. But what is nice here is that, everything, there is interaction everywhere. So the interaction is not just infinitesimal at a point X, but it's everywhere. So you need to have information in all the space Rn in order to compute the fractional mean curvature of the set E at the boundary, at any point at the boundary. As also one should expect, so this is just the principal value definition. So you also have that if the fractional perimeter converges to 1, then you recover the usual mean curvature, so which can be guessed or can be expected, just as what we said before, that also the fractional perimeter approximate nicely the classical perimeter function. So this expression is for the non-local mean curvature is very nice and can be simply used somehow to obtain also comparison principle, which is not the case for the case of the classical mean curvature. So because if you want to compare the mean curvature of two sets which touch it at their boundary point, then you simply have to compute the difference between their signed indicator function, so which is of course very nice. Okay, so there are just very few interesting properties. So as we said, so this is that the non-local mean curvature so is invariant. So if you make any translations and any rotations, you recover your same quantity, and also it scales like r to the power minus alpha. So the smaller the set is, the larger the fractional mean curvature is, exactly as it is. The smaller a ball, the larger it is curved, of course. And also we have an interesting comparison principle somehow, which is global. In a sense, somehow, if I have a set E1, which is contained in E2, and then I have, which touches at a boundary point, of course, then the one that is contained inside is somehow more curved, and therefore, so its mean curvature is larger than the one that contains the set. And this is the usual comparison principle, which can be done for the infinitesimal mean curvature, so which is the classical mean curvature. So this can be done locally because it is locally defined. So you do not need any information from everywhere, but you only need the information exactly at that point or in a neighborhood of that point. But for the non-local mean curvature, you need informations to have informations everywhere. And so this remark is saying that, in fact, the fact that E1 is contained is E2 is necessary. And because this is somehow very easy to check by just looking at the symplectic expression of the fractional mean curvature, that if the two sets, they do not contain to each other, then you can easily build the two sets for which the comparison principle will not hold. So let me just give you examples of non-local minimal surface. So non-local minimal surface. So if the surface is smooth enough, then you can use this expression, which is a kind of non-local divergence of the normal along the surface. So And in this case, you can see for the plane, so x, y. So if you look at the expression of the mean curvature, it's quite clear that y minus x is sitting on the plane, the vector, and nu is perpendicular to the plane. So for the plane, it's very easy to see that it is 0. So the helicoid also, but this requires more technical computation, was obtained by Del Pino and Cinti, who found that in fact the helicoid is also a non-local minimal surface as the classical mean curvature. So they are minimal surface, very natural. Yeah, so this was found by Cinti, Davila, and Del Pino in 2016, who proved that in fact, so the helicoid is also a minimal surface, non-local minimal surface, of course. Yeah, yeah. So the natural question is maybe whether we can have some which are non-trivial, so some which maybe cannot just obtained by just doing some computations, direct, easy computations. So in fact, there are, and the only two that I know are obtained using perturbation techniques in alpha. So in a sense, if alpha is close to 1, so you are converging to the non-local to the classical mean curvature. And these surfaces, non-local minimal surfaces, globally defined on R&R, were obtained by Davila, Del Pino, and Way, and which are rotationally symmetric. And somehow they obtain something that looks like a non-local catenoid. So it is still an open problem to know if you have a catenoid for the full range of alpha. And the other one can be also extended periodically in the vertical direction, which is asymptotic to a cone of revolution. So a cone, you cut just the origin. And so you have, of course, a classical zero mean curvature. So these are the techniques they use to make perturbation when alpha is close to 1 to build up these minimal surfaces. Okay, so what about now the constant? So what I was saying, constant and non-zero, non-local mean curvature. So there are also some which in dimension, for instance, 2. So you have parallel lines which are not perhaps immediate to see that in fact they have constant non-local mean curvature. Circles, of course, they do have that, and parallel lines, you can go in dimension 3, the spheres and the cylinder. So all of these are somehow kind of maybe parallel lines, parallel planes, and cylinders. So these are parallel lines, parallel planes are generalized slabs. So in a sense, one can expect slabs to have constant mean curvature, and maybe extend them periodically to see if it's possible that they have constant mean curvature. But in a sense, they have, and they are very easy to compute. So for instance, let me just take 2 lines. If I take 2 lines and I want to know if in 2 dimensions they have constant non-local mean curvature. So just to see the interaction between line 1 and line 2. So this is also very easy to see that if I look at, if I just pick any point, maybe on line 1, so which is x, and I simply assume that, so this line 1 is just the E1 direction. Then when I integrate over the line 2, so so you simply make it's just a very simple integral. You just look at a one direction integral, and then you compute this. Yeah. So of course, one the normal, so you see, I'm always looking at the normal, so maybe you see, that's why I have one here, which I should not forget. And therefore, if I compute this, I exactly get a constant expression, so which is very ugly, but still constant. Yeah, so which is right. Okay, so we know that parallel straight lines have constant mean curvature, which is not the case, of course, for the classical mean curvature. They have zero mean curvature. And so one is therefore led to understand somehow some kind of rigidity results, maybe that if they are the only one or not, which have this type of symmetry properties. But then let me start with just one of the first rigidity results that are also interesting to state before going to unbounded cases. So the rigidity of the sphere, or maybe a characterization of the sphere is, so the first one of the most interesting results, of course, that allows to develop many ideas, many techniques, such as moving plane methods in the PD theory, is the Alexandra result, or maybe work, which states that, in fact, the unit sphere is the only bounded connected surface with non-zero constant mean curvature. So this is a very interesting result, and which also, of course, applies to connectedness, which requires connectedness. And so what is going to happen in the non-local case, which is a quite natural question. And in this case also, we obtain exactly somehow the same result as Alexandrov, except that here one does not need your surface to be connected. And the reason is that, so any connected component, any two connected component will interact together. So you cannot just have information for one connected component without having some information on the other. So all these interactions allow somehow to see that you do not need connectedness. So no matter how they do disconnect it, if they are compact, then they become connected and become one sphere. And this was a funny result that was obtained independently, so by my collaborators, and at the same time by Sirawolo, Figali, Maggi, and Novaga, and in fact we submitted without talking to each other. We submit the paper in the same journal at the same period, which appeared in the same issue, of the journal. So it's very strange. Okay, so let me just sketch a little bit the proof of the Alexandrov's moving plane argument. Of course, in the non-local setting, it's in fact very convenient, somehow rather easy. Okay, so the idea is somehow just to maybe here to consider any set E connected or not. And then you fix one direction, which can be called E1, and then you make the reflection, and then you start translating the reflected set. And if you do that, of course, so you see E lambda is the reflected set, and I wanted to translate E lambda in the direction of E1 to come and hit E, and then I want to see some situations where I can say, okay, so I can have some information that, okay, if these things happen, then I must have the E lambda, so the E must coincide with its reflected set. And these two situations from which, if I use them, I can, and the fact that you have constant mean curvature, I have some information, are, the two cases. So which are the usual case. So whenever you have somehow some kind of interior touching, and also maybe a kind of non-transversal touching. So which means the two sets, the boundary of the two sets, they share the same normal. So in a sense, they share the same tangent vector. And the idea is that, in fact, if any of these two happens, and in fact it happens always for the first time, at least you have one of the two. Anytime these two happen, then my set E is exactly my reflected set. And if this is true for one direction, it will certainly be true, of course, for any direction, and therefore my set must be a ball. But then what is interesting for the fractional case is that if you use the symplectic expression of the mean curvature and the fact that the kernel is decreasing, the kernel, which is mod x minus y to the power n plus alpha, is decreasing, then here is a very nice way. So how I mentioned it before, that it's a very nice way to make a comparison. So in the classical case, you need to write down locally a PDE, then you use maximum principle, Hopf boundary point maximum principles, and things like that. But in the non-local setting, you can just simply do it directly from this expression of the non-local mean curvature. And the only thing that you need to use here is the fact that you are just you have the x minus y to the power n plus alpha. So the kernel of this of the mean curvature is a decreasing function. So the way it is just interesting. And in the interior touching, then you need to make something more. You need to use an ingredient which is more difficult. So that you can differentiate, but it's really not easy because you are differentiating the PV integral, so a principal value integral, and this is where the difficulty relies. The only place where the difficulty relies. And once you are able to do that, then you use the fact that both terms are zero, and then you can immediately also conclude that your set E is the set E lambda. And you see here that there is no need of even mentioning connectedness or nothing. Everything is based on the fact that you are using the sign indicator function, which is very nice to use if you want to compare the mean curvature of two sets. Okay, so let me just quickly go to the graphs, classification of graphs. So with constant non-local mean curvature. So these are the this contains a lot of open problems which I wanted to tell you about. Okay, so the classical mean curvature. So as I said before, when you look at it, it is kind of operator when it acts on graphs, a quasi-linear elliptic operator. But the non-local mean curvature has a kind of very strange also expression, but still it's a quasi-linear non-local operator of order alpha. And maybe one can simply see in both cases, if the gradient is small, then you see the mean curvature somehow is exactly a kind of an operator, so a linear operator, which is very nice. Translation invariant, so it's the Laplace operator if alpha is 1. And therefore, one can expect many interesting things because this is a nice expression also that can be used for comparison principle and in particular, higher order regularity theory, to obtain regularity estimates. Once you know that you have a Lipschitz graph. Okay, so there are open problems which are quite interesting and difficult, which is the Bernstein type problems. So which states that if you have non-local minimal graphs in Rn that is not a hyperplane, and which was first proved in by Bernstein in 2D in R3. So, and also later on De Giorgi and then Almagren and Simons, who also presented some cones in dimension larger than 8. But these are the cones where that Bombieri, De Giorgi, and Gusti somehow showed that in fact they are global minimizers, and therefore you have a counterexample. And those are the Simons cones. So in the non-local setting, the answer is no. So the Bernstein type result was obtained by Figali and Valdinocci, open for dimension larger than 3. And so this is the only thing that is known up to now in this direction. So another thing maybe that I would like to talk about is the rotational symmetric hypersurfaces, which are known to be the cylinders, the unduloids, the spheres, and the nodoids, which were found by Delaunay. And these surfaces are obtained by rolling an ellipsoid and then tracing the focus. Then you rotate around the z-axis, and then you obtain something. And this surface that you obtain is in fact a constant mean curvature surface, which are of course a very good rigidity, which is a classification, which is of course interesting. And so the question that we were interested in, in the last years was whether such type of surface can be obtained in the case, of course, of in the non-local setting. And there are somehow, let me present. So there are 3 results somehow which are obtained using bifurcation theory. So I said before that 2 lines have constant non-local mean curvature. And in fact, you can bifurcate 2 lines in order to obtain also a constant non-local mean curvature. So this is a 2D kind of Delaunay surface, which does not exist somehow in dimension for the classical mean curvature. The cylinders, one can bifurcate. So maybe if you see that I'm just talking about this result from dimension to dimension, but in fact, it's not easy to, it was not somehow easy and not clear, of course, to do everything once. Somehow the cylinder, one can bifurcate from cylinder also to a Delaunay, to an unduloid. But even if if you have slabs also, you can also bifurcate from slabs to have this doubly periodic constant non-local mean curvature. And all of this somehow was obtained so in different joint works. So for the perturbation of 2 lines in the cylinders, which is a connected surface, so which is more interesting. And also you have this doubly periodic hypersurface, which was obtained by my PhD students, and which also provides disconnected non-local mean curvature surface. Okay, so one usual interesting problem is that, of course, you talk about bifurcation, but then you bifurcate from cylinder. Then when you go from cylinder, you pass through Delaunay, and then you go to spheres, and then from spheres, then you go to other non-embedded constant mean curvature surface, which are called nodoids, but still let us just stay here. So this global bifurcation is well known in the case of the non-local, in the case of the classical mean curvature, but in the case of non-local mean curvature, it's a bit tricky and remains open. In fact, one is obtaining something that you go from cylinder to unduloid, and then from unduloid to a string of non-round pearls. So, oops, and so these non-round pearls, so there are results that tells that in fact you cannot have a tangent spheres, and we will see that maybe tangent sphere do not probably necessarily find also a string of pearl made of round spheres do not necessarily have constant non-local mean curvature. And so there are results that says that allows somehow to say this. So Davila, Del Pino, Di Piero, and Valdinoc so obtained that somehow when you can minimize to obtain some kind of unduloids, but then you can bifurcate from there to obtain something that looks like some kind of surfaces with separated volume, which looks like a string of pearls. But so since the results do not show regularity or anything, so it's very hard to say how these sets they look like. So this was a problem. So that is quite interesting, and somehow is just trying to understand. So what is going to happen when you make a global bifurcation? Are you going to obtain some spheres or not? But in this case, so what we find so far is that in fact, if you take these periodic spheres, and then if the radius r is very large, then they do not have constant mean curvature. And we conjectured that in fact they do have constant non-local mean curvature for r, for any r. So what we could see is that they do not have constant non-local mean curvature if r is large. But however, it's possible in fact to perturb these a little bit and to obtain something which have constant non-local mean curvature. And so the argument is based somehow on the implicit function theorem. And this is somehow quite makes a quite big difference so between the classical and the non-local case. So how much time do I have left, or do I not? I do not have anything anymore.
1 or 2 more minutes, Mohamed.
Okay, thank you. So 1 or 2 more minutes. I'll take 2. Okay, so okay, so let me just simply say, maybe share with you this slide. So in which case that maybe if we consider a Brownian motion or maybe Levy process, and then we look at so the expectation of the initial condition. So when they at the process. So in a sense, I am just solving the heat equation with the initial condition U0, which is assigned the characteristic function of the set E. Then when I look at when I shake the set a little bit via the mean curvature, via the diffusion heat flow. If it is the classical one, or maybe if it is simply a general Levy process, then I have an approximation of the mean curvature if alpha is between 1 and 2. So 2 is the Brownian case, which is the classical heat diffusion flow. But in the non-log, I can also recover the non-local mean curvature motion also when alpha is between 0 and 1. And these are the classical results. So the first approximation was obtained by Bench, Merriman, and Osher, and Evans provides an interesting proof, a rigorous proof for the algorithm of the Bench, Merriman, and Osher. And in the case of the non-local setting, so this was was first considered in Caffarelli, Souganidis, where somehow they were able to approximate the non-local mean curvature motion by a kind of Birch, Merriman, Osher algorithm, and they show that in some viscosity sense you can approximate them. And recently, so there is a result, so in which is somehow parallel Evans result for non-local diffusions of smooth sets. Okay, so these are what I wanted to tell. I think I do not have, okay, so this is the last slide. And so this is the last slide. So let me just keep it like this, the time that we share questions. So it's remarks and open problems, so everybody can read it. And write in the chat questions at the time that we close so the meeting. Thank you very much.
Okay, excellent. Thank you so much, Mohamed. Beautiful talk, beautiful subject, beautiful questions, hard questions. And thank you so much for sharing those ideas and those beautiful problems with all of us. So we have some time for questions, comments, remarks. You can either speak up or write here in the chat. So while people are maybe formulating their questions, I have one. I'm always curious about how stable those non-local or fractional results are as you approach the full diffusion. Let's say when alpha goes to 1 or 2, depending on what kind of fractional you're using. Do you have stability results for those problems?
Well, I think so. We didn't really add these in our work, but of course, for instance, so you will lose some information. Well, I would not say some information. For instance, if you know that two parallel lines have somehow constant non-local mean curvature, so if alpha is tending to 1, so they will not be constant, but they will be minimal. So the constant goes to 0. So you may, in general, get some time of results. So, for example, for the unduloid, it's clear. So when alpha is converging to 1, it's stable. So you will find again the same unduloid in the non-local case. Yeah. So, but it's not always the case. Yeah.
Yeah. Because I think it's interesting. Yeah, it is interesting, those fractional results, especially when they somehow reveal even further information about the field diffusion process. Once you let alpha approach 1, there are things that if you were working with the full diffusion system, you wouldn't be possible to recognize. But once you tackle this family of problems, some pictures may appear, which are really beautiful and very interesting.
Right. In fact, indeed. For example, so this is even so. Let me just, so maybe if you look at the slides, this slide now, then you look at, for example, the modulated lamellae, so which comes from the D block copolymer, so in which here you have kind of energy which comes with a classical, diffusion energy, or I would say the classical perimeter, and a kind of non-local interaction. Then you see this type of configuration, some kind of phase separation in block. But these are pictures that the fractional setting captures.
Exactly.
So in the classical case, you know, you do not have this kind of non-local or maybe interaction, which brings you a kind of separation into block. Yeah, so I think it's very interesting, and it captures somehow different configurations that appears, of course, naturally. Yeah, so in at least yeah, in some patterns, yeah, in from biology.
Excellent. So so there is here one question here on the chat. Maybe you can look at.
So he says, okay, so Radu, okay. So non-local curvature where the kernel is integrable. Okay, so which, so you know, if you look at the definition, or maybe what I was calling symplectic definition of the fractional mean curvature or non-local mean curvature. So you can replace the kernel 1 over mod x minus y by any kind of function. So you can replace by any function. Somehow, if your set now is bounded and your kernel is integrable, so you only have, you do not need to define a signed distance function, but you are just integrating in the exterior. And you have to be very careful whether this is finite in Rn. Yeah, so integrability maybe could be very fine to use, but still, in this case, if you are non-singular, if you are integrable, then it's somehow much easier to do in some cases, but I'm afraid that you may not capture some kind of phenomenon which I was presenting now.
Okay, excellent. There's also here a question. Yeah.
Okay, so could you please expand on the roulette of the conics by Delaunay? Okay, so let me see here. Okay. Okay, so the Delaunay, in fact, so you take, if you take somehow says, he says you take an ellipsoid, and then you make a roulette on it. So you turn it around. So you turn it, but you trace only one focus because it has two, but you fix only one focus, and then you draw the line where the one focus is going, and then this gives you a line, and that line, you rotate it around the z-axis, and this gives you a rotationally symmetric axis. And those surfaces, for example, if for example, if this is a circle, if this is a true circle, then somehow you only have a kind of a cylinder, and somehow this is the reason why. So we're saying that you can only have these possibilities. But what is not easy to see is, of course, the classification to return. For example, if I have a rotationally symmetric constant mean curvature surface, then they fall into this family of Delaunay. But this you can study ODE because it's rotationally symmetric. Therefore, it's an ODE problem which can be also studied. So yeah. So what is interesting is the observation that when you from the roulette of a conic, you recover all possible from the roulette of an ellipsoid, then you obtain all possible rotationally symmetric surface.
Awesome.
Sorry, I hope I answer your question.
Okay, great. Is there any further question or remark? So if not, I, on behalf of the PD and application webinar. Thank you all again for coming. And I will pass the floor over to Stanley Nelson for final remarks. Thank you.
Yeah, thank you, Eduardo, and
bye-bye.
Thank you for that very interesting talk, Mohamed.
Thank you.
And thanks everyone for coming. Yeah, we will post more talks to our schedule soon, so stay tuned and look for the announcement in your inbox also. So hope everyone has a nice day.